Hey everyone, so as you said, I'm Laurie Kirk and I'm going to be talking to you about obfuscating Android applications using purely native code. As I said, Laurie Kirk, I'm a reverse engineer at Microsoft. I specialize in cross-platform malware analysis with a focus on mobile threats. I also run a YouTube channel called Laurie Wired where I do a ton of different reverse engineering and analysis of malware. And today I will be representing myself as a security researcher, not representing Microsoft. So for anybody who wants to follow along or take a look at these slides, I have this QR code right here. All this is going to do is link you to GitHub, where I have the slides currently, and after this presentation, I'll be uploading all of the supporting code in case you wanted to try obfuscating some Android apps yourself. So let's just get right into it. So the only difference between this application, which is uploaded to VirusTotal and has about 5 detections from different antiviruses, and this application, which is entirely undetected, is that part of the second application is actually written in native C++ code. So this brings me into our agenda today for how we can actually use native C++ obfuscation in Android to obfuscate our applications and actually remove antivirus detections. So we're going to be actually creating a purely native application together, and then at the end, we're going to take that native application and try and mask our API calls to the Android framework to produce an even less detected application that's written in pure C++. While we're doing this, we're going to be using the Anubis Android malware. So the source code is available for you online on the VX Underground website. So you can download that, but I have a completely defanged, benign version of this application that we're going to be using during our testing process. So this is the code that we're going to actually be translating from Java over to native C++ code. And at the very end, we're going to upload our finished application to VirusTotal and see if we were successful in removing some of our antivirus detections. Just a big disclaimer here, I have never uploaded this to VirusTotal, so kind of fingers crossed, I hope this actually works, and I hope we actually reduce our detections, but I will be just as surprised as you guys. Now let's get into some of the background of our obfuscation and our native code inside of Android. First of all, the primary programming languages inside of Android are going to be Java and Kotlin. This is going to be your managed code, but what you might not be aware of is that you can actually include additional native C or C++ code inside of your Android applications as well. This is going to be code that is compiled to run on a particular instruction set architecture. So you can include these additional compiled binaries inside of your Android application file as well, if you're trying to run probably particularly optimized code on a specific device. You might be saying to yourself right now, does C++ really equal obfuscation? Is this actually obscuring the functionality of the application? You might actually be surprised. In Android, this is completely true. So this is the same application from that first application with 5 detections in VirusTotal. And literally all I did here was just add a stub executable of C++ code inside of my Android application. And some of the smaller antiviruses already stopped detecting this application. So that might make you think, maybe we're onto something here. That's honestly kind of pathetic that just adding the stub executable will actually reduce some of your detections, but let's go into some of the further advantages of native code obfuscation. Another things that help our native code obfuscation is it's more challenging to reverse engineer than regular Java applications in Android. Basically, you're forcing the reverse engineer to actually read your assembly code and possibly decompiled C code inside of IDA or Ghidra, instead of using one of the popular Android decompilers and pretty much being able to view all of the original source code in Java, basically as the developer wrote it. Additionally, it requires a lot more knowledge of the Android ecosystem. For example, you have to know what the JNI is and how to use it. So remember the JNI, it's actually the Java native interface, and it's used a lot in Android, and we're going to be using this towards the middle of this talk, so keep that in mind. Finally, you're able to remove support for particular processor architectures. For example, one really common thing that I see in Android is malware authors will try and remove support for x86, since a lot of Android emulators are running x86, so they're trying to prevent reverse engineers and analysts from actually seeing the full functionality of their application. So now we've seen this, and we know some partial native code actually works. So what I wanted to know when I started this journey and started working on this talk is, how far can we actually go with this? Can we make an entirely, possibly native Android application without any Java code? And that's exactly what we're going to do today. So first step is we're going to try removing our Java entry point. So this is going to be the main entry point of the application that is inside of every single Android application you've probably ever analyzed. Then we're going to take all of those normal Java methods, and we're going to translate them over to native C++ code in our new entirely native application. Finally, I'm going to go into how we can conceal some of our Android API calls, doing some special magic at the end. Let's get into the first step, which is going to be removing our Java entry point. In case you're not familiar with Android applications, this is the standard structure of an Android app. On the left-hand side, you can see our Android manifest.xml. What this is doing is it's defining all of the potential entry points that are inside of our actual Android application. So if you see that activity tag right there, every single one of those different tags is actually pointing to a defined Java class that is inside of our Android executable. So that is going to have the actual implementation of the Android application, but the manifest, so keep that in mind, that's also important, is going to point to all of those defined Java classes as the potential entry points of the code. So instead of just me talking at you, I'm going to be doing a lot of examples today, so let's do hands-on and let's just decompile a normal Android application and see how easy it is to find this entry point and find the decompiled Java code. So I'm going to open up JDEX. JDEX is a really popular free online decompiler. And we're just going to take a Hello World application, and we're going to look at the entry point. So I have this precompiled application. This .apk file, if you're able to see it there, actually stands for Android package, and this is the primary compiled binary for Android applications. So every single application running on your Android device actually has a corresponding APK file underneath that contains the actual source code. And now remember that really important Android manifest file that has all of our entry points? We can actually go on the left and do the package explorer. Open up this Android manifest.xml, and here are all of the defined entry points. Now remember that activity flag? This is actually defining the name of the corresponding Java class that's going to be defined within our application. So we have this string here, com, example, hello world native, since this is just a hello world application. And then this main activity here, so I can find this by going com, example, main activity. Here's all my Java code. Really easy, right? Do you remember how easy this is and how trivial it is to actually discover the entry point and read this nice, pretty Java code? So this is actually decompiled, but basically like reading the source code of when I wrote this application. So this is actually how, let me go back to my slides. This is how we usually find our entry points within Android and read the Java code. But what I want to know is this possible to bypass? Because this is super easy to do. If you're a reverse engineer, you've done this 100 times, and you can find the code no problem. So could we actually confuse other reverse engineers by trying to remove this entry point and potentially all of the Java code? Yes, we can, and that's exactly what we're going to do. This brings me into something called native activity. So when I started out, I didn't really know where to begin with trying to create a purely native application, but I stumbled across this class that's actually defined inside of the Android framework, and this is generally used for gaming applications since they're using really intensive, trying to do very efficient stuff, and they're trying to do a bunch of different graphics on the screen. So you have this native activity, which actually is defined inside of the Android framework that we can use for our obfuscation. And all of this does is it has an additional metadata tag. This allows us to define an actual native binary that could potentially include all of the C++ code that we don't want to define in Java anymore. So the new flow becomes something like this. We have this native activity, which remember is in our Android framework, which has this onCreate method, which is very common in Android apps. It's basically going to be the first method that runs once your new class or activity is actually instantiated and started. But now we have this weird additional thing inside of this strange native app glue, and I'll get into what that is in just a second. But it's going to call this a native activity on create method as well. But the main thing to take from here is our new main entry point is going to be entirely defined inside of C++ in this Android main method. So going further into what the application glue actually is, this is part of the Android NDK, or the native development kit. And this is going to now be responsible for all that normal Java code that is actually usually keeping the context of the application, or actually what state the application is currently in. For example, what's the current activity that the user is interfacing with right now. Now we have this special class called the native application glue that's going to be keeping track of all those different data structures for us. So this handles your application context, and this is going to be the really special class that actually calls that user main, or that Android main method that I talked about in the previous slide. Additionally, this defines an event loop listener. So if a user is trying to click their application, enter code, type, click buttons, anything they want, this is actually going to be looping and listening for all of those events so that it can respond accordingly, even though we don't have any normal Android Java code that is actually responsible for this. This is all C++ on the back end. This is a little bit of the context structure defined inside of the native application glue header. And you can see this is handling all different callbacks and events for potential state changes within the Android application. And as I said, now all we need to know is user code goes inside of Android main. So pretty much a lot of this is actually defined already for us. So that's absolutely awesome. And we can use that and just put all of our native code inside of this Android main function. So let's actually do that. So I'm going to pull up my code once more. And we have this actual native application right now. So let me pull up my other activity. All right, so we had our previous activity up, and you see it had the Java entry point within it. So now I'm going to be pulling up our purely native application, and we're going to be defining that Android main method that's going to have all of our C++ code defined inside of it. So I'm going to get this building so we can actually run this. And let's take a look at what we have. First of all, if you notice, we have this Android main method. Remember, this is the really important one I was talking about. And we have all of this user code defined in here. Right now, I just have some code that's going to print some nice colors to the screen. But if we take a look at this Android app pointer right here, this is actually defining the actual state of our application instead of what Java code normally does inside of the Android framework. So if I right-click on this, hopefully you're able to see, and I go to the declarations, this is the actual Android application glue class that I said that was so important, that's now handling all of the different back-end code that we need to actually run this application fully in C++. So this is defining the structure. So this kind of replaces the application context. If you're familiar with Android, you might know the context. So now, just think of this Android app structure as the current context that's going to allow us to do a lot of different fun stuff. So let me just run this application, and we're going to build it. And I actually want to show you exactly what's happening, and then we'll throw this into JDEX, and we'll see that we actually don't have the entry point defined. So here we have, it's a beautiful application. You see it's just black. Now we have some colors. So yay, fun stuff is happening, and now this is entirely defined within just our C++ code inside of that Android main method. So that's cool, but let's throw this into JDEX and actually take a look and see how that's different from this code right here. Here we go. Let me just generate the APK file. So remember, all of this is happening live, so you're just watching me program, so I hope nothing breaks and everything actually does work. So here is our new APK, our Android package. Let's go back to our JDEX instance. Let it load. Remember the really important Android manifest file that's defining our entry points? Now this is actually pointing to this Android app native activity. Well, this doesn't actually exist inside of our code because this is actually pointing to that class definition inside of the Android framework. So now if we look on the left-hand side, we see some package name right here, but this class actually doesn't exist at all. And if we look in our metadata, it's actually defining our native library that's going to include the Android main method that's actually defining all of our native C++ code. So if I was a reverse engineer and I opened up this application, I would be really confused and probably kind of annoyed, and it would take me a lot longer to figure out what is going on. Because if I look on the left-hand side, there's also no Java code. We just have these build configs, but there's no main activity with our Java code defined. So that's kind of interesting and confusing. So let's go back to our slides. So we've successfully masked the actual entry point. This is the starter to our new Anubis application, which remember was that Android malware that is completely defanged for this talk. And we've successfully got our first initial code down. There's no entry point, but now there's actually no functionality inside this application except printing pretty colors. Additionally, we can remove some of our resource files. I removed a lot of the actual Android library code as well as some assets just to further minimize our application and make even less analysis surfaces for any reverse engineers who are trying to take a look at this. Next, can we actually remove the Android manifest? Wouldn't it be amazing if we could have an application that had no entry points defined? I really wouldn't want to reverse that. So can we remove this? The answer is no. This is actually the one file inside of an Android application that you cannot remove. So it's kind of the core file that actually defines to the system what to do with it, how to run this application, how we can actually use this. But we were successful otherwise, and this is just some really cool stuff that you can actually do with native Android applications. This is drawing a lot of cool shapes to the screen. Not sure if anybody is familiar with Raw Draw Android, but this is another graphics-intensive application that we can write in native code. So that's really cool, but the focus of this talk is obfuscation and malware. So now we can write malware that draws really pretty shapes to the screen, but that's not really very fun. So let's actually take some of our Java methods that are inside of our actual Anubis application that is defanged, and let's translate them over to C++ so we can actually get some functionality inside of this purely native app. You might be happy to know if you're a developer or not, but Java and C++ are not too different from each other. I mean, well, somebody might yell at me for saying that, but a lot of syntax is really similar if you're writing native code in Android. So this is just printing out the Fibonacci numbers to the screen, but the only difference between these two methods for this particular case in Android is actually just going to be the logging statements in Android while it's printing out those numbers, since it's actually invoking the Android framework here. So that's cool. Now we can draw shapes and we can print the Fibonacci numbers, but what if we actually want to manipulate the device? We have to use something called the Android framework. So what is the Android framework? It's basically just a collection of APIs, classes, methods, variables that we can call inside of our Android code as Android developers so that we can actually interface with the underlying device services and hardware and actually manipulate the device and potentially do some shady behavior. This is how we're going to actually interface with anything important inside of Android. And if you remember that really important JNI, or Java Native Interface, this is going to come back to haunt us, because this is how, if we're stuck purely in native C++ code, we need to be able to invoke actually the Java framework that's inside of the Android platform. So we need to use the JNI to actually invoke Java code from C++ code here. This allows you to do the reverse as well, but I'm just looking at invoking Java from C++ today. So think JNI, think the bridge between Java and C++. So now let's go hands-on one more time, and let's actually take a Java method from our Anubis code, and let's translate this over to native C++ and see if we're successful. So I'm going to open up my other application right here. And let's pull up the Java method that we're actually targeting today. So for reference, this is actually part of the defanged Anubis application. This is a lot of code right here, all defined inside of Java. This is the actual original Java code. And if we go up here, I'm going to pick on one particular method. Remember how I said that a lot of malware authors will try and remove support for x86 and try and test if they're running on an emulator? This is exactly what they're doing here. They're basically just trying to detect heuristic presence of an emulator with this isEmulator method. So let's take this method and let's just translate it to C++. So I'm going to copy this here. And let's go back into our Android Studio. I'm actually going to close out my old instance because Java is a real resource hog and tries to eat all my resources. And let's add a comment here of this is the method that we're trying to translate. So all we need to do is we just need to start writing this in C++. Pretty simple. So I'm going to do bool, since this is returning a Boolean value, copy our method name, put our parentheses, and start this method. But the only thing is, remember we need to use this Java native interface. So the Java native interface is actually going to allow us to communicate with the Java code. So this is actually going to need an additional argument inside of native, which is going to be the pointer to the Java native interface. And through this env pointer right here, we can actually invoke different JNI methods to call these Java classes. So let's find the actual build class. The build class is again inside of our Android framework. So what we need to do is we need to pull up the Android framework and take a look and actually find this class. This is the class that we're going to be trying to take a look at. And inside of our code, it's trying to find the fingerprint, which is just another device heuristic for detecting an emulator. So I'm going to take my env pointer, and I'm going to actually define that class and find it inside of my native code. So the type is JClass, or Java class, and I'm going to call this build class. And then I'm going to take my env, which is actually the pointer to the Java native interface, and I'm going to use this find class method. So if you have any questions about the Java native interface, best thing to do is just go to the documentation. This defines all of our JNI functions and types and structures that are available to us. So if I search for find class, for example, this will tell me exactly how to use this. So this is going to locate the build class from the Android framework. So find class, and then all we need to do is actually pass in the class name. But this needs to be our fully qualified class name, so let's copy this. And I'll paste in my Android OS build, but it's actually going to require me to use slashes for this instead of dots. That's just the syntax that the JNI likes. So now we've got a reference to the build class, but we actually need to get the fingerprint field from inside of that build class. So I'm going to declare a new JFieldID, which is a Java field ID, that's going to say which field I'm trying to reference inside of this build class. So I'm going to do JFieldID, and I'll just call this fingerprint ID. And then again, we need to use this structure of pointers to all of the JNI functions. And I'm going to do getStaticFieldID, which is nice. It does some autofill for me. And what we need is the class name that we just defined. So where is it located? It's in that build class. And then we also just need to pass in the actual name of the field that we're trying to reference, which we were trying to get fingerprint. And it fills it in for us. So the last method here is this is actually defining the signature for the fingerprint. So if we take a look at the documentation and we search fingerprint, this is actually a static string that's defined inside of the field class. So we can open this up, and we're finding our static field, and it is of type Java lang string. So that's the actual signature for this field. So now we've got the actual field ID, so we actually need to get the value while the application is running. Once more, we can use our env, and we're going to do get static object field, and then this is going to be getting the actual runtime value of what is the fingerprint value for this particular device. And we will pass in the build class that it's located in, the actual ID that says which field we're looking for, and we should be good to go. So we actually want to return a Java string, and we're going to store this inside of another variable so that we can actually do some manipulation and actually do some comparing inside of here. So I'm going to define a new J class, and I'll call this fingerprint Java. And I just need to typecast this to JString, sorry. So now this is of type Java string, but we're actually in C++ land right now. So we need to convert this over back to C++ before we can do any actual comparisons with this. So I'm just going to define a new string in C++, and we'll just call this fingerprint, because now we've actually gotten it, we're in C++, and we can do whatever we want to it now. So we'll just convert this over to a C++ string, because if you're trying to work with the Java string in C++, they're actually in two different formats. So C++ is going to be like, what is this string? This isn't an actual string, and I don't know what to do with this. So I'm going to do get string UTF-chars, and then we'll pass in our fingerprint. Now we're finally in C++ land completely, and all we need to do from here is do some string comparisons. And we can do something like this, and we'll compare it to whatever they're doing up here, which is the word generic. And then that was the return value, so something like this. So this is translating part of the fingerprint code from Java over to native C++ code. So already you might be thinking this is a lot more complicated than just writing this in Java, so maybe that's a little bit harder to read. But instead of going through and translating all of this and watching me do that, that would take a long time. So we're just going to go back to our code. All right, so now you've seen the process of actually translating the Java code over to C++. Keep in mind, if you look at the entire application, let's put yourself in the shoes of you've been looking at this for maybe like 3 days, and you've gone through and hand translated every single Java method inside of your Anubis application over to native C++, following that kind of process, and now you have all of these JNI calls that are actually invoking the actual functionality of this application. And we're going to take a look at what the completed product looks like at the end as well. But one thing to note, these JNI calls, if you didn't notice, they were actually plain text strings. So this is really easy to read, and it's also really easy to hook. A lot of reverse engineers understand JNI calls, and they're really common targets for trying to hook them while the application is running and actually try and read their values and see exactly what's happening. So this is really easy and really very easy to bypass. So as I said, they're commonly hooked, they're plain text strings, they're easy to reverse engineer. So what if we want to be stealthier? What if we actually want to avoid having all of these plain text strings inside of our application using the Java native interface? Even though we have kind of a partially obfuscated application that doesn't have an entry point, it's still really simple to actually throw this into Ghidra or IDA and understand the full possibilities that this application can perform. So this gets me into my next talk, which is going to be hiding our API calls via the binder. We're going to be doing a case study today, which is going to be trying to dial a phone. So we're going to be using the telephony manager, and this is using something called intents, which are basically just messaging objects that are sent in between the device to try and do something like call the telephony manager service, which is just sitting there waiting for these messages to come in so it can do the proper corresponding behavior. Since from our user application, we can't actually directly make the phone dial a number or anything. We have to use this telephony manager service that's going to be doing it on the back end. So the telephony manager service is able to actually handle these requests and events and dial the phone accordingly. So let's do some knowledge time and explore the actual binder that's going to be passing these messages back and forth between our user application, all of these different services that are currently running on the device that are actually able to trigger all of this behavior and make the phone actually do something. Okay, so what is the binder? Basically think the binder is responsible for all inter-process communication and remote procedure calls inside of the Android ecosystem. So basically if I have one app over here on the left-hand side and then one app over here on the right-hand side, and my app needs to communicate with each other, it needs to go through the binder to actually be able to send these messages back and forth. Similarly, this is how we can communicate with services on the device. So you're not aware, but on the back end you have all of these different messaging objects sending stuff back and forth between each other, between applications, between services, and this is how the actual functionality is getting invoked. You may be familiar with something called intents or messengers or even content providers, but these are actually, if you look on the back end, wrapping the actual binder implementation. So this is just calling binder on the back end, even though as an Android developer, you might be using the actual intents or messengers. Content providers are going to be if you're trying to interface with a database or anything. All this is actually wrapping binders, and even the Android interface definition language is still just wrapping binder objects. So what I was thinking is, do we have to actually use these really popular classes that are just wrapping the binder? Or can we possibly bypass these common targets and actually just implement the binder directly, even though maybe it's a little bit less safe, but at this point, we're probably malware, so I don't think we care that much. Let's dive even deeper into the binder and its implementation and see if this is possible. So first of all, the binder is actually implemented as a driver inside of the Android kernel. This is a bit of the Android source code, which is available online for anybody to read, which is really awesome and really fun. So this is actually defining some messaging queues, and if you just explore the source code, you'll find these queues that are sending these different objects back and forth, and they're able to respond to them. So every single individual class is actually defining one of these binder objects that's able to handle its defined messages and invoke certain device behavior when it receives the actual messages. If we continue to dive into this source code, then you'll actually see a structure kind of like this. So basically you have your binder driver in kernel space over here, and this is able to be invoked by different processes and services. So I have my user app on the left-hand side, which has its binder object, and it uses this really important method called transact. And keep in mind, you're going to want to remember that method because we're going to be using it a lot later on. And this is actually allowing the binder to allocate some additional space inside of the target service. So this is done for security reasons, so that only the binder driver is actually able to communicate between processes, since I don't want my non-privileged user app over here able to actually modify the system services. That would be really bad. So the solution is using the binder. And then once that service receives this new allocated memory inside of its address space, it's able to actually perform this onTransact method and respond to this invocation. So the whole process looks something like this. The binder allocates memory in the target process. That target process handles it with this onTransact method, and then it's able to write a response back to that space, and then the binder is in turn able to return that response back to the calling process. So you might be happy to know that you don't actually have to know all of this if you're trying to do some obfuscation, since you don't actually have to invoke the binder directly unless you're doing direct IOCTL commands. And you can only do these if you're running as root, which is honestly kind of lame, so I didn't want to make that the focus of this talk. So I'm going to be showing you something we can do in our userland of our application to actually invoke this on a non-rooted device. So that's kind of nice. You don't have to know as much background information of the binder, although it's still pretty interesting, so it's still fun to know. Now I want to actually transact with the existing services on the application. For example, that telephony manager service, where we're going to be doing our case study to try and dial a phone. But we actually need to know, how do we invoke this? Where do we even begin? And what is actually handling these different invocations inside of the Android ecosystem? That brings me, after a lot of exploring around the Android architecture and code, to this class called Service Manager. So Service Manager is kind of like another wrapper for the binder, but it's designed for these different system services, such as Telephony Manager, and it's actually returning the corresponding binder objects for each different system service. So I think we should actually use the Service Manager to be able to invoke some of our different Telephony Manager service code. So that's exactly what I tried to do. We have this import of the Service Manager, and I'm trying to actually get a Service Manager object and call one of its methods, but we're getting this error that we cannot resolve the actual symbol, and no matter what I do, trying to debug, fix my build or anything, this isn't helping, and we're still getting this problem. So the reason behind this is This actually, in more recent versions of Android, is changed to a hidden API. So this is designed only for system service use. So other system services can actually invoke this service manager, but we can't invoke this, which means if we can't invoke this, we can't call the actual binder, which means we can't invoke our telephony manager service and dial our phone. So this is kind of annoying. So this is impossible for us to use. Or is it? Actually, if we use something called reflection, this is going to allow us to dynamically invoke different classes. And the coolest thing about this, which is honestly crazy to me, is that reflection does not respect hidden APIs. So even though they tried to hide this API from us, we can still get it. I mean, it's not really that big of a deal because they're probably thinking, why would you want to? Because this is a little bit less safe and secure than doing it the proper way, but probably everybody in here doesn't really care about that and doesn't mind doing things the wrong way for fun or whatever reason. So now, if you're able to see that class.for name invocation right there, this is actually our reflective call. We're getting a handle to the service manager class, which is no longer hidden to us. And we're actually able to invoke that, and we don't get any more errors inside of this. So this is really interesting, and now we actually want to be able to see what services we can actually invoke and if we can get our telephony manager service. But now, how do I know what the services are, and how do I actually call this? I don't know what services are running on the device. Let's go hands-on one more time, and let's go inside of the Android source code, and let's actually find out. So I'm going to pull up our source code here. I magically already have the service manager up and running for you so that you don't have to spend the time it took me to find it. But this is this call to get service. And we saw a lot of different methods trying to call this with a bunch of different strings in order to get the actual system service they're looking at. So I'm just going to look at the references here and see, can I get a better idea of what to pass to this system service, since it's returning the binder object that I want to be able to use for my interprocess communication to invoke the dial method. So I click on it, and I'm going to scroll down. I see that's my definition right here. And I can see some strings, activity, and I see this interesting context.networking management service, and quite a few other plain text strings here, and then more services. So that to me is like, hey, this looks pretty interesting. Maybe we can find our defined services here. So I'm actually going to take this context object, and let's see if we can find all of the services that are available to us. Let me close this out. And we can just kind of explore the actual code inside of this application. Let's pretend we've spent a lot of time reading through all of this code. And we scroll down here, and I see, bingo, we see a ton of different services defined as strings, and that getService method, if you remember, was actually looking for the string, which was the name of the service. So I wonder what our telephony manager service is actually called. So I'm just going to search it in here. Maybe we can find it. Keep going, keep going. Here we go. Now we know the telephony manager service is actually called phone. So that's the actual string that we need to pass to our application so we can interface with this telephony manager service finally. So let's go back to our slides. Now we know all of the different services that are available to us. And if we keep going down and looking at all the different services that are running on the device, you're going to see something like this. These are the actual services. So these are all of the things that are invocable via the service manager. Now we actually want to invoke them. So now we need to go to something called parcel objects. And parcel objects, pretty simple. They're basically just kind of wrappers around different metadata that can be passed to these binder objects. So if you're trying to look for a particular method or interface, you can pass that in the form of a parcel object, and it's going to contain all of that data and maybe the arguments for your particular method that you're trying to invoke. So you must write which interface you're trying to target, which in our case is going to be the telephony manager interface, and then you must write the method arguments, and you're additionally going to use these parcel objects to return the actual return value of that method that you're trying to invoke. And also remember that really important transact method that was actually invoking some of the different binder interprocess communication. This is actually going to be the thing that takes our parcel methods, parcel objects, and actually does the actual method call and performs the actual process communication. So this is going to receive another parcel object in return, and you can actually read that returned parcel to get the return value. And one thing that's really important, keep in mind, this is actually going to take the method code. So it's not going to be taking the actual method name like we used in our Java native interface. You know, we had to pass those plain text strings that were saying exactly what class we want to call, exactly what method we want to call. This is actually avoiding some of that. So at this point, I got pretty excited because I was like, oh, cool, we don't actually need to use the method name anymore. So let's actually do that. So I'm going to pull up another Android application, and let's just write that. So this is going to be actually trying to invoke the telephony manager that we were actually looking for, and then it's going to be invoking that dial method. So what I've done here, this contains the same code that I talked about before. Remember, we're using that reflective call to get a handle to the service manager that's going to give us this binder object that's actually going to let us perform our interprocess communication and actually remotely invoke that target method. These are our parcel objects, as I mentioned. We're just storing the actual interface that we're trying to invoke, which is this telephony manager. And then, if we take a look at the actual dial method, this is requiring one argument, which is going to be the phone number that we're trying to dial. So we actually just need to perform the actual transaction right here, since we've got this setup code already complete. So we take our binder object, this binder right here, and we're just going to binder.transact. And then if we want to take a look at the documentation, we can see here's our binder class. And I'm going to take a look at my transact method, which is going to take the method code, the parcel object, which contains the parameters for the target method, the reply, and then any flags for the transact call. All right, let's actually do that. So for our transact code, when I started writing this, I was like, what the heck is the transact code? I don't even know where this number is coming from. So I took a long time trying to explore the Android source code to see if I could find if there was some constants that actually told you what the code is. Let me save you some time. There's not. So I kind of just did some guesswork here. So you're going to do some guesswork with me. I'll pull up the telephony manager interface here. And here's our actual dial method. So this is containing our phone number that we want to invoke and actually dial. This is actually the first method defined in the interface. Okay, so I was thinking, well, maybe the code is actually 0 or 1. So I could actually just try that and see if it works. And I'll give you a hint, it actually does work. But does it actually start as 0 for the index or 1 for the index? So, I don't know, show of hands, who wants to try 0? Okay, show of hands, who wants to try 1? Okay, I think 0 won by far. So let's just see if it works. So we passed 0 for the code, our first parcel object, our reply parcel object, and then don't worry about the flags, this is just invoking the normal transact method. And I'm going to get this running on my emulator, and I'm going to hope that my emulator actually works. So we're going to give this a second to start up. The Gradle is actually building the application right now and compiling all of this and doing just a ton of this work on the back end. My computer is really hot right now, but you can't feel that. All right, so our application's running. And it's just printing this to the screen, nothing. So sorry guys, you were wrong. It's not 0. So let's actually pass 1 to this and see if we actually get the dial here. Rebuild this and let it run. Should be quicker this time. There we go. Now we actually dial it. So the answer was 1, and yay, we were correct the second time. Okay, let's go back to our slides, and let's talk about, we did this in Java, so I'm not sure if you were paying attention, but that was actually a Java application. But we need to do this in C++, because if we go back and we try and remember what our actual goal was, we were trying to take the benign Anubis source code and translate it from Java over to C++, but also trying to mask our API calls. I'm not going to make you do this with me because I won't lie, it took me kind of a long time to do and it was very irritating. But if you do this, it's going to look something like this. So this is getting a handle to our service manager class, but we're actually doing this via the Java native interface instead. If you remember when we translated from Java to C++, we had to use all of these JNI methods to actually perform our invocation. And then I'm not sure if you can see, but on the bottom part there, we're actually creating our parcel objects and doing the binder transact call. And one really important thing is that method at the bottom there actually passes a 1 in. Now, we don't actually name what method we're trying to invoke anymore. So if somebody was trying to take a look at this and see exactly how this worked, they would have to understand exactly what that 1 stands for and means within the application, which requires a lot of background knowledge, so they might just be thinking, I have no idea what this is doing, which is a win for us if so. So let's go to our test time. What we're going to do is we're going to actually take the application that is completed. This is going to be our full native source code of the benign Anubis application. It's also going to include our telephony manager invocation via direct binder messages that has that code that defines the dial method for us. And then we're going to also upload this to VirusTotal and cross our fingers that it actually worked and we have less detections right now. So I'm going to get that going first, and then we'll decompile this while it's loading. Let's go over to our VirusTotal, and I'm going to choose the file. So I showed you some of the intermediate steps for this, but for the sake of time, I had to precompile the file. But as I said, I have not uploaded this to VirusTotal. So let's see if we can find our APK, which is our Android package. And then we'll go to Anubis, purely native APK, and we'll get this uploading. So this is uploading now. Oh, not quite yet. I have to hit confirm. Okay. While this is uploading, I'm going to stop this, and I'm going to throw our completed code into JDEX, and let's just kind of go back over exactly what we did. I've got my APK here. This is the same APK that we're currently trying to upload in VirusTotal. And let's double check and make sure we've removed all the Java code successfully. So I go to my resources, open up the Android manifest one more time. We're still good. We've still got our native activity as the entry point. Remember, this is completely avoiding all of our Java code. Doesn't exist on the left-hand side, so as a reverse engineer, I would not know where to start with this. But eventually, I might realize that there are some additional libraries in here, specifically inside of the lib folder, which is containing all of the supported instruction set architectures that this application will actually run on. So we'll just pick on one. This .so, shared object binary, is actually containing all of those native C++ methods that we saw that we were in the process of translating earlier. And if we open up this application, we can find this actual native binary, but I already have it open in Ghidra for us to view. This is the actual full decompiled transact telephony service native implementation. So remember, this is getting the handle to the service manager, actually performing those different message calls. This is the thing that's actually performing that dial method that you saw that is actually just bringing up the phone number that you're passing to it. So let's take a look at this and see how annoying it is to read. First of all, if you remember, this is the Java native interface pointer. So we can actually name this here for easier use and able to view. And we had our find class, which is getting our parcel object. It's calling this static method, and it's actually getting the fingerprint stuff. Not the fingerprint. It's actually getting the binder object here. And we go down here, we're passing the phone number to these parcel objects, and then we're saying exactly which class we're trying to invoke. So we've got our binder class right here, which is leading us up to our transact method call, which is performing the now remote call for this method right here. This is the actual call to it. So this is going to be a lot more challenging to read than if you did this in regular Android code. You would create a new object that says it wants to actually invoke the dial method, and that's going to be really easy to read because it's actually calling the Android framework, passing in the exact string, plain text, class name of what you want to invoke, passing in the method name that you want to invoke, and then performing that call. So put your reverse engineering hat on again and think, which one would you rather read? Would you rather read the plain text dial method, or would you rather read this weird, first of all, it's going through the Java native interface, passing in this pointer to it, calling this transact method. Maybe you don't even know what a binder is. I mean, a lot of people don't. It's kind of obscure Android knowledge if you just have fun with Android. And then you're passing in this code that's going to have to force the person reading this to know that this one code is from this iTelephony manager interface, and one actually corresponds to the dial method. So hopefully you're getting how complicated and confusing that is, and the amount of knowledge you have to have about the Android ecosystem to even understand what it's doing. So let me go back to our actual virus total. We were successful. So remember, at the very beginning of this presentation, we uploaded this application that was part of the Anubis code. This was the same in every way, except it was defined in Java, and it had the normal Java entry points. This is the same code, but translated over to native C++ using the Java native interface to invoke any of its actual underlying behavior. And this has the direct binder invocation for our telephony manager dial method call. So we were successful. We actually reduced our detections by 4. I think all of the big names are actually gone here, so we just have one detection. Man, that trust look person is very smart because they're still detecting it, but it's still pretty good. We reduced our detections by a lot. We're basically effectively able to make this application run as if it were an entirely new application, when all we did was actually just use C++ code and the Java native interface. So let's go back to our slides. So let's kind of summarize exactly what we did and look at our success. So first of all, we can actually encrypt these Java native interface methods more if you wanted to encrypt those plain text strings for any methods that are not invocable via the telephony manager service via binder messages. So you can do that, and that's not the focus of this talk, but I highly recommend doing that if you want to further obfuscate your applications. And then this avoids all of the plain text strings that might be inside of your application. Now let's finish our summary. We have our purely native application that does not have an entry point, and we have no pretty Java code that's able to be just thrown into that JDEX decompiler and understood really easily exactly what the application is doing. So this is going to really challenge your human analysts in particular, because human analysts, I've noticed in Android, really hate looking at native code. They like to look at the Java code because, I mean, who wouldn't? I'm not going to lie, I like looking at the Java code. It's easier to read, but they're going to be really annoyed at you already if you're doing this inside of your code. Additionally, you're going to further frustrate them because they have to actually look at these direct binder invocations, which they might not know exactly what this is even doing. And finally, the additional benefit here is that a lot of reverse engineers are commonly hooking these JNI calls and all of these intent objects passed between different applications. But now you're actually bypassing those intent objects, so they would have to know to actually listen for the direct binder calls in order to listen to what you're doing. And a lot of automated sandboxes are definitely not doing that. So to close, will we see these techniques more? We have a lot of techniques here for the purely native code, translating Java code to native code, and then the direct binder invocations. The answer is, I don't know, because you saw some of the process of rewriting this. It's actually really hard, and you have to really understand a lot about Android to be able to just take all of your Java code and rewrite it there. So maybe we'll see a little bit more of this, and if we do, it's actually really successful at obfuscating our application. And it's really exciting and kind of the next phase of some Android obfuscation that hasn't been done as much before, which is crazy because it actually does reduce your antivirus detections by a lot, as you saw. Now go make some native Android applications with direct binder invocations, and you should be able to solve this. So thanks so much, everybody. I'll open it up to this in case anybody wanted to download the slides or anything or see some of the materials. As I said, I'll be posting these after the talk is done. I didn't want somebody taking my app and uploading it to VirusTotal before me, so that's why it's not there yet. But if anybody has any questions now.
Okay. Are there any questions? There are a few questions. I'll start maybe here at the front.
Hi, thank you very much for the talk. Really very interesting. I was wondering about the first app. Well, one of the first things you did in the code was to hide the entry point. Mm-hmm. Could you go back to the manifest of that first Hello World, but the one with the hidden?
Yes. So this is, I think, this is the first example.
Probably. Can't you see anything on the application line of the manifest there? Normally, you should have an entry point as well there, which goes before.
That's a good point. That's a really excellent point. So you don't actually have to have the application subclass inside of here. It's an optional thing. If you do have the application subclass, this is going to run before the actual main method right here, but it's completely optional. So in this case, I didn't include one, but that's really commonly used for malware that's trying to unpack itself. Maybe you could specify that as the native activity. I'm not sure. I didn't try.
Okay, and the last quick question, when you're compiling your native application, you need the NDK?
Yes.
To compile it? Okay.
So I can maybe show you right here. I have this full CMake lists right here, and the NDK, remember, includes our native application glue, and that was handling all of the different context of the application. So if you don't include your own version of that native application glue, you definitely have to include the NDK so you can compile this for native and actually have your context handled.
Okay, thank you.
Yes, have you tried to push this kind of application on the Play Store? Because I know there is like a Google validation process that could be annoying. So did you try?
I didn't try because I didn't actually want to push malware. I mean, I know it's defanged, but somebody might not realize that. So the Play Store for Android is not as picky as it is for iOS, for example. So they very, very commonly host actually super obvious malicious applications, even though they're really good about taking them down really fast. But maybe somebody can try pushing something. I probably won't, but I think it should work because if you saw that one application that was drawing the shapes to the screen, Raw Draw Android, that's a legitimate application. I'm not sure if he's pushed it to the Play Store, though. But you could check.
Okay, thanks.
So I have two quick questions. First of all, do you know of any other hidden API that is only accessible through the reflection?
So there are a lot of hidden APIs. I can't think of any off the top of my head. There we go. But additionally, if you look at any of the defined private methods inside of a class, even if it's not hidden, you can still use reflection or the Java native interface to invoke those. So it's a surprisingly powerful random bit of knowledge.
Yeah, it's surprising that it's not possible to import it, but it's still there to me.
It's technically by design. Mm-hmm. I looked it up, but I don't think it's technically a bug.
And another question, by skipping the intents and using this binder directly, does it reduce the amount of lines in the logcat, like in the logging system? Or if I would attach a logger to an Android device running this malware, would I see the calls to dial and telephony manager?
I don't think so, because the intents have additional logs that are always being written to logcat. It's a great question. I didn't actually check. Maybe chat with me after this and I'll just test and see.
And finally, did you think about, instead of using C++, which is really well decompiled by Jidra, did you think about using other, more obscure compiled programming languages, or even what would happen if you would implement a virtual machine, like maybe even the Java VM in C++ to run obfuscated Java code? Would that make it even harder to?
I mean, yeah, you're trying to make reverse engineers hate their lives, but yes, there are a lot of VM-based obfuscators that are always implemented, I think pretty much usually implemented inside of C++ that have completely additional defined instructions. If you wanted to write the whole JVM, feel free inside of there, but it might be quite a challenging thing.
And then you don't need to rewrite your Java code anymore.
Yeah, I mean, you can do that. Those are just different obfuscation techniques. Currently, with the state of how Android is and the analysis process of it, it's just enough, literally just to use the JNI like I did. But definitely there are other obfuscation methods as well, or you could even combine a lot of them.
Okay, thank you for the answers and thank you for the talk.
Okay, was there any more question? Okay, I think we have time for one more.
Hi, thanks for this very interesting talk. I just, I mean, I see that this is a great way to bypass detection, and I was just wondering, have you like come across any malware, Android malware in real life that actually just like migrates all of this attacks or these functionalities to the JNI or to the C++?
So I actually have not, and that's a big question for me of why not? Is it literally just because it's hard to do? And I think that's maybe my answer. It's also a teeny bit more inefficient because you're adding the overhead of the Java native interface. But if you're writing malware, do you really care about performance? So yeah, no, but maybe we will now. Or at least in a few years, not sure.
Okay, thank you very much, Laurie.